my side. I'm really proud to be here today and be in the position to tell you a bit about the work that me and my co-founders are pursuing at our startup HamburgAI. And this talk will be about deep learning in healthcare, in particular on the challenges of developing a decision support system for prostate cancer detection. Yeah, I guess I do not have to tell you about the fascinating potential of deep learning, in particular for image analysis. However, I really like this picture, and I like to show it in the beginning of my talk. Somebody told me that it's a good idea to show some cute animals, puppies, or whatever in the beginning. However, I really like it because you can see that so far deep learning is already possible to distinguish quite similar patterns in pictures, in this case muffins from chihuahuas. And actually, I think that the complexity of such a kind of classification task is also found in healthcare. If it comes to distinguishing malign cancer from benign cancer, so dangerous from undangerous cancer types, it's quite a similar task. So this also already brings me to what the company does and why we do it. We are a Hamburg-based startup founded in 2017, and we want to transfer deep learning technology to the medical field. When I started, I thought, yeah, well, nothing is closer than doing that because the advantages are so obvious and the benefits are so obvious. However, it seems to be a bit more difficult, and this is also what I'm going to talk about later. Why are we doing that? Because we think that improving the accuracy in medical image analysis and thus in diagnosis is of great benefit not only for a company or for a single doctor, but for society. So we think we bring together return on investment with return on humanity, and I guess that's a great thing to do. So far, we are developing the product which is developed the furthest is a product called Prostate Carcinoma AI. It's still under development, so we're not done yet. But this software is a software to assist during the detection of dangerous prostate cancer. And this part, or this kind of software is called computer-aided diagnosis. So why did we choose prostate cancer? Because it's such a big thing. Actually, most of men will suffer one or another kind of prostate disease during lifetime. The older you get, the more likely you are to develop inflammation or cancer types. And the difficulty for the doctor, in particular for the radiologist, so the doctor who does image analysis, is to distinguish between two kinds of cancer. The first, a benign prostate cancer, or the so-called harmless pet cancer type, and this is what I actually name it, how I name it. Most of the cases, we are glad because this is such an abundant case. 92% of all suspicious cases are actually benign cases. You have, however, the risk to overdiagnose this, so to take this kind of harmless cancer for a dangerous cancer type and thus do overtreatment, coming along with some kind of complications, bleedings, unnecessary biopsy, unnecessary surgery, and cost for the healthcare system. The second type of cancer is the really dangerous one. It's the dangerous predicate cancer, or carcinoma. In 8% of all cases, you will find this type there. And for the patients that have a prostate carcinoma, really important to detect it with a high accuracy and as early as possible, because this will influence the healing chances greatly. This is then how it actually looks like, and you see that, yeah, for the non-radiologist's eye, it's quite difficult to distinguish the two. So I'm a trained biochemist. I am somewhat familiar with medical questions, but I'm not an expert in analyzing this kind of image too. However, for the benign prostate cancer, you see some kinds of hyperplasias, which are really harmless types and do not have to be followed up by surgery. Whereas the malign prostate cancer is really dangerous, and in most of the cases you will have further treatment there. So this is all about distinguishing the two in these kinds of images, and the images you see here are actually MRI images, MRI images, which magnetic resonance images, which visualize different structures within the body. And we are in the lucky case that the radiological societies have aligned on a structured way of analyzing these kinds of images and how to do the acquisitions of these images, and this is called PIRATE. It actually gives quite a good specificity, so a good chance to detect a dangerous cancer as such. However, in almost every 10th patient, the cancer is not detected, and this is really dangerous because the treatment should actually take place. Coming more into the terminology of deep learning, we're talking about a classification problem here. In the original medical data, it's a 5-class classification system that reflects the risk of having a dangerous carcinoma from 1 to 5, with 5 being the highest risk. So what we do is, first, we do an image registration. This is necessary because the MRI images that we analyze are not just a single image per patient, but it's actually almost 2,000 images per patient that come along in series that represent different kinds of structures. So it's a multi-parametric MRI, meaning that you do different series. And what you see here, the first image is the T2W, which is the standard series to show the anatomy of the pelvis. The second image is an image series that is created to visualize the diffusion within the tissue. And what you have to do is you have to align them, you have to bring them together. And this is what is done first during the image registration, amongst other tasks. The second thing that we do is we want to detect which area we have to analyze for detecting cancer subsequently. So first we search for the prostate because we want to find cancer of the prostate. So first task, segmentation task, where we do a pixel-wise or voxel-wise analysis and produce a mask for the prostate. Third task, we search for different anatomical subregions within the prostate because this determines which of the different series is actually the first to be analyzed subsequently. And the fourth task, and this is actually the most important task, is then segmentation of carcinomas, so segmentation of the dangerous cancer itself in the prostate. Yeah, this is what we're currently doing. We are convinced that the potential of these computer-aided diagnostic systems is really tremendous. But actually, there's only a number of startups that already provide commercially available solutions. and this is shown here just really briefly, with potentially or probably zebra, analytic, or arteries being the most prominent cases. Yeah, so how comes? Why hasn't deep learning taken over medical imaging yet? And this is what I say yet. So far we identified 4 major fields of, initially I thought problems, now I would rather call it challenges, which are data set, data interoperability and standards, privacy issues, and regulatory issues. And I'm going to tell you a bit more about these 4 fields. So data set first. Probably you're familiar with this publication that came out in 2017, where a group of researchers produced a deep learning-based software that was able to classify skin lesions at the same level as a dermatologist does. It was really a great breakthrough and gained a lot of attention. However, I have to say they had a huge data set. They used 130,000 images that were classified originally with 2,000 diseases. However, this dermatologist level is more about classification of all these types in only 2 classes, malign or benign. So a huge data set. And this is actually not what you usually have in the medical field. So we see that there are some challenges, and they actually belong to two groups. Limited amount of data, because you, as a normal person, as a startup, not being employed by a hospital, you normally don't have access to medical data. It's high sensitive data. It is stored within the medical facilities, and so access to large quality data sets is usually limited. The typical number of samples that we see in this medical field is more in the range of thousands and not in the range of 100,000 as shown in this big paper. Furthermore, it's not only that you have limited data, it's also that the annotation that you get from the medical staff is limited. So we think, or we know that the less data you have, the more effort you have to put into a annotation, into a good annotation, so into detailed labeling of regions, sub-regions, and carcinomas. And this means that you have additional costs that are necessary because an expert has to do that. Yeah, so what do? Like, we have now these challenges. First, limited amount of data. What we try is first reduce the complexity of the medical problem. And there was this animation. So the prostate consists of several zones that play a role in the guidelines that the Radiological Society has published, how to analyze MRI images. And it's actually, several regions and quite a difficult task. So what we do, for example, is we start with a simple task first. So we first find the borders of the prostate and use this mask for the subsequent model, which then analyzes the regions and does the segmentation of the regions. So we use more information, and we provide more information to our models in order to reduce a bit of the complexity. And the same is also true, for this multi-class problem. I said that originally it's 5 classes. What we actually do is we say that the class number 3, where the doctor actually says, I don't know, it's unclear, doesn't tell anything. So you actually want to get rid of this class 3 and rather classify suspicious parts of the prostate in either dangerous or not dangerous. So we reduce it to a 2-class problem first, and then move on to this 5-class problem. Yeah, And the next point is data augmentation, and now I see that there's not so much time left. Usually what you do as well is you do data augmentations in order to create an effective training set, and we do the same. It's just that you have to keep in mind that not all possible augmentations that you would usually use on an image task are also meaningful in terms of, or in the medical field. So keep that in mind. For example, the patient usually lies on his back when he gets into the MRI. So not all kinds of rotation, flips, and other things might be a good idea. Another thing, and I guess this is quite common, applied transfer learning, use pre-trained networks with data that is publicly available, for example, from challenges, and then do your own learning subsequently. Yeah. The problem with data annotation is shown here. So this is what we actually get from our collaboration partner. So just a marker somewhere within the structure telling you there is a carcinoma and this is what you have to find. However, what we actually need is a really detailed pixel mask throughout the whole 3D data set, telling me which pixel belongs to the structure or doesn't belong to the structure, and this is what we have to do subsequently with a teleradiologist, creating some cost in case of 200 cases used for training, approximately 24,000 euros that come on top. Yeah, the other parts are a bit, or I can talk about them a bit quicker. Data interoperability and standards is a problem in the medical field. However, we say that it's important for the startups to actually focus on the areas where there are guidelines from the medical societies that at least tell the radiologist how the data has to be taken, so data acquisition with fixed parameters, slice thickness, resolution, and all these kinds of things to reduce variability there. And second, also standards for interpretation of this medical data, because only then you will also find acceptance from the medical field in the solution you produce. Otherwise, they tell you did whatever you thought was necessary or useful, but actually doesn't reflect the standard. So concentrate on the fields where this is actually given, and we find that for the case of prostate cancer in this PIRATES guideline, or also in case of MANA cancer, so breast cancer with the BIRATES guidelines as well. Privacy issues. The kind of data we use for training is actually patient data. So it was somebody in the MRI, somebody's images, and you have to take care that you really work in a secure setting here. So the sensitive patient data must be protected. We only use anonymized data. We secure a safe data transfer way. We have developed a data protection concept and strategy. And in most of the cases, it's really a good idea to ask the radiologist to ask a patient for his explicit consent in using his data for this kind of task and software development. Last issue, regulatory issues. And this is actually a big deal when it comes to financing and investments into your startup, because the way for a medical device into the market is a long way, and this somewhat reflects the complexity that you find there. In particular, it's really the case that these computer-aided diagnostic systems are medical devices, meaning that the medical device regulation is the legal framework you have to work with. It means a long time to market because a lot of things have to be fulfilled unless you can actually sell your product to your customers. Meaning you have to prove efficacy and safety of the product, and this actually sounds easier than it is in reality, because you have to compare to the existing solutions and really have to prove that no safety issues come along with using your product. So most of the startups actually say we only we are only an additional piece of the jigsaw puzzle in helping the diagnosis. So we are more assistants, and then we really think that the software can do the job on its own. Second, and this is the more organizational topic, you have to prove, or you have to certify your quality management system, which is also time consuming. And you have to provide a technical documentation file in order to earn the CE mark necessary to bring the solution to the European market. It's expensive, it's time consuming, but we think nevertheless it's worth it. Because I said in the beginning, the benefits are so clear, and they are not only of economic on the economic side, but they are really also on the humanity side. And thus we think that it's really, why hasn't deep learning taken over medical imaging yet, rather than a question. Borders and restrictions always are active in two directions. So we think once you made it, and once you really earn a CE mark for your product, bring it into the market, it's such a great chance. And thus we think it's worth it. We pursue this way, although we know that things are slower, more time consuming, when you're active in the medical field. Yeah, so thank you for your attention, and I'm really looking forward to the questions you have.